As we've seen, capacitors and inductors don't contribute to average power. However, that doesn't mean that they don't have an effect on AC power, but we do need to broaden our definition of power. In this video, we'll introduce complex power, which has an imaginary component. Before we talk about complex power, I want to introduce a couple of new terms: apparent power and power factor. These terms are related to the equation for average power that we've already seen. In terms of the peak values of voltage and current, the average power is the maximum voltage, V sub m, times the maximum current, I sub m, over 2, times the cosine of the voltage phase, theta sub v, minus the current phase, theta sub I. Since for sinusoidal signals with no DC offset, the RMS value of the signal is equal to the peak value over the square root of 2, this is identical to the RMS voltage times the RMS current times the cosine of theta v minus theta I. Different terms in these equations have their own names. The apparent power is the term in this equation that multiplies the cosine function. Apparent power, therefore, is the product of the RMS voltage times the RMS current, which is equal to Vm times Im over 2. The units of this are the product of voltage and current, which is generally referred to as watts. However, we want to make sure we don't mix up apparent and average power, so we give the apparent power units of volt amps, abbreviated VA. The cosine of theta v minus theta I term is called the power factor, and it's unitless. Cosine is an even function, so the power factor won't provide any information about the sine of theta sub v minus theta sub I. The power factor, therefore, is denoted as being either leading or lagging to indicate the sine of theta v minus theta I. If current lags voltage, theta v minus theta I is positive, and the power factor is said to be lagging. Conversely, if theta v minus theta I is negative, the current leads the voltage and the power factor is denoted as leading. Complex power is a way to express all of these parameters in a single complex number. By definition, complex power is equal to the voltage phasor times the complex conjugate of the current phasor divided by 2. To take the complex conjugate of a complex number, you just change the sign on the imaginary part of the number. In polar coordinates, changing the sign on the imaginary part of a complex number simply changes the sign on the phase angle of the number. That means that the complex power in polar coordinates is V sub m at an angle of theta sub v times I sub m at an angle of negative theta sub I divided by 2. When we multiply complex numbers in polar coordinates, we multiply the magnitudes of the numbers and add the phases. So the complex power is V sub m times I sub m over 2 at an angle of theta v minus theta I. In rectangular coordinates, the complex power is denoted as P plus J times Q. Since P is the real part of S, it's sometimes called the real power. As we'll see in the next slide, P is also the average power. Q is the imaginary part of the complex power. It's called the reactive power. Now let's do the math to relate the various parts of complex power to our other power parameters. Complex power is just a complex number, which can be expressed in either rectangular or polar coordinates. The magnitude of the complex power is Vm times Im over 2, which is the apparent power. As I've already mentioned, we use special units, volt amps, to denote apparent power to make sure we differentiate apparent power from average power. The real part of the complex power is Vm times Im over 2 times the cosine of theta v minus theta I, which is the average power. The units of average power are watts. The imaginary part of S is Vm times Im over 2 times the sine of theta v minus theta I. This is the reactive power. Reactive power also has units of volts times amps. But to avoid confusing this with either of the other two types of power, reactive power is assigned units of volt amps reactive, or VAR. The various types of power are often represented graphically as what is called a power triangle. Since the complex, real, and reactive power are all now considered to be complex numbers, the power triangle is indicated in the complex plane, with both real and imaginary axes. Each element of complex power is indicated by an arrow in the complex plane. The complex power, S, has a magnitude Vm times Im over 2 at a phase angle of theta v minus theta I from the real axis. The average, or real power P, is the projection of S onto the real axis. Its magnitude is the magnitude of S times the cosine of theta v minus theta I. The reactive power, Q, is in the imaginary direction, and its magnitude is the magnitude of S, Vm Im over 2, times the sine of theta v minus theta I. Understanding the differences between real and reactive power is important, so I want to go back and take another look at instantaneous power in the context of real and reactive power. The instantaneous power is the product of the voltage sinusoid and the current sinusoid. We've already seen that we can express P of t in this form. However, with a little more trigonometry and algebra, we can express the instantaneous power as the sum of cosine and sine functions, each of which have zero phase shift. Graphically, the two components of this equation look like this. This cosine function is always positive, which means that the power associated with this term is always absorbed. The average value of this function is Vm times Im over 2 times the cosine of theta v minus theta I. So this function results in the average power of the signal. The sine component of the instantaneous power has zero average value, so there's no actual power dissipated by this signal. The power that's absorbed when the power is positive is exactly balanced by the power that's generated when the signal is negative. This signal corresponds to the reactive power, and it's representing what the energy storage elements in the circuit are doing. Capacitors and inductors don't dissipate any energy. All they can do is store the energy and then return it to the circuit, which is exactly what this sine wave is doing. The reactive power, then, is representing the energy being stored and released by the energy storage elements in the circuit. The average power is representing the electrical energy that's converted to non-electrical work, or the dissipation of electrical energy. In this class, non-electrical work is done by resistors. They convert electrical energy to heat, so our average power will be due to resistive elements. In general, however, average power can be used to pump water, turn motors, and so on. As an example of complex power, I'll use this circuit from the average power video and determine the complex power delivered by the source. The last time we worked this problem, we found out that the source current was 10 over root 2 at an angle of 45 degrees, and the average power delivered by the source was 250 watts, which was exactly the same as the average power absorbed by the resistor. The average power of the capacitor was 0. Now let's calculate the complex power for the source. Complex power, S, is the product of the voltage times the complex conjugate of the current over 2. The voltage is 100 at an angle of 0 degrees, and the current is 10 over root 2 at an angle of 45 degrees. To get the complex conjugate, I change the sign on the phase angle, so that becomes negative 45 degrees. Divided by 2, so S is 1,000 over 2 over square root of 2, which is 500 over root 2, at an angle of minus 45 degrees, 0 plus negative 45 degrees. Now, the average power is going to be this magnitude, 500 over root 2 times the cosine of this angle, negative 45 degrees. Cosine of negative 45 degrees is 1 over root 2, so this becomes 500 over 2, or 250 watts, which agrees with our previous answer. That's the average power. The reactive power, however, Q, is still this amplitude, 500 over root 2, now times the sine of this angle, negative 45 degrees. So this becomes 500 over root 2. The sine of negative 45 degrees is negative 1 over root 2. So this becomes minus 250 VAR, volt amps reactive. So the capacitor has no average power, but that doesn't mean that it has no effect on the power in the circuit. It has a reactive power that's negative 250 VAR. We can use complex power concepts to improve the efficiency of power transfer to a load. This process is called power factor correction, and that's the topic of the next video.